times, but
Okay. So yeah, here we start talking about the details about those level 1 and level 2 data products and exactly kind of the steps, or at least maybe not exactly, but estimate of what happens in those steps. Okay, the raw data comes off, well, that comes off the telescope to FITS files, a level 0 FITS file, and here at the bottom is kind of a listing of the extensions in a level 0 FITS file for a 1074 waves data file. It has 6 extensions here. So the first index just there is the number of the extension, then a name, which means something to us. There is a data type in our files for you guys. Phi is everything that you care about, but we have various calibration files that we use in the processing. So this is a science file that has the corona in it, a date and time, a wavelength, and then we do this multiple camera. It says which camera is on band at the time. So a waves file is basically a minimal observation in order to be calibratable, right? So for the 3 wavelengths, you have to have one image where RCAM is on band and one where TCAM is on band, so that you can do all the subtractions that you need to do. Each array at this point is a shown there 1280 by 1024 for the physical size of the image, but you've got 4 for the polarization states, which at this point are not IQ, U, and B. They're this mixed up thing. And then 2 is for the cameras. So even though RCAM is on band, you'll get two camera readings there. You'll get the RCAM that's on band, and then you'll get the Continuum and the TCAM for that image or for that extension. Okay, okay, so that's the raw data, and this is actually what the raw data looks like for one particular extension here. I'm taking the center line. RCAM is on band on the left, so those 4 images are the 4 different, these mixed polarization states are basically all intensity. But you can see the corona, and then you have a background that's pouring in TCAM that we're going to subtract later. The one other thing in reading the raw data that we do is that outside the pipeline, Ben has a process of finding glitches that are anomalous frames. By frame, I mean one exact extension, one in one camera in one polarization state. Right? Something went wrong just for that split second that we were reading that, taking that image, and so they're removed. Now the waves being kind of minimally, they have the absolute minimum data required to be processed. So if there's a bad frame in a waves file, that waves file can't be processed. But for the synoptic, usually there's like 4 repeats of everything that are averaged together. And so we can recover from missing a bad frame here. We just remove the bad frame and continue on. The averaging will just not be quite as good. But it's found outside the pipeline, so it's not done in real time. So we have to take the data, it'll be processed that night or whatever, and the data will be available when we're taking data. The data would be available the next day, but the frames are found sometime later, and then a reprocessing is done at some point in the future, and then those bad frames will be removed. And that's recorded here with this REM frame, so you'll know if there's any frames that have been removed. Yes.
Why can't you remove bad frames in the waves program? What's the reason behind that?
Because for every extension, so for instance, in this guy, if there was, say, intensity in that first extension wasn't there, you'd have no RCAM intensity, right? So you'd be you couldn't process that, right? It wants to have a on band and off band for every camera, and then you So you can do that subtraction, and we'll talk about these steps later, but you have to do a subtraction, and then you average, combine the two cameras. Now I could not combine cameras basically, and like, for instance, decide, oh, I'm going to still try and process this file, but now I can't use the ARC when RCam is on band, and I just take whatever happens in TCAM as the value. But you'll see in the processing, averaging the cameras really helps. And so the file, I don't think would end up having very high quality, right? So theoretically you could, but I don't think it would look very good. Whereas when you have the synoptic file, you have kind of, 4 or more for each camera, right? You have more chances that it's okay. And here's an example bad frame. On the right, you can see that there's a little halo outside the occulter there, right? And so here's for the very next file, that same exact extension of polarization state and camera is what it should look like.
You have an automated way to detect these bad frames, or is it by eye? Or
Ben has a like a machine learning type.
Yeah, it turned out it didn't work as well as just looking by eye. We're gonna name our automated system Lisa. Keep her in Hawaii.
Okay.
But it turns out that they're actually relatively easy to spot in a little so.
Yeah. So Ben basically makes a list and then puts it in a directory for me, and then the pipeline just reads that and says, okay, for the file I'm reading now, are there bad frames? Let me remove them, and then move on. The next thing we do is a quality check. So I mentioned this because in some of the listings, you might see files that we had observation for, but that there's no level 1 file for. And so these are basic metadata checks, kind of sanity checks, that this is a reasonable file. And so if something's happening, like it reports a temperature that's way out of range, or it has different data types in a single file, right? So it's like half the file is science data and half is a flat or something. Basically things that we don't expect to happen. We just fail the file and don't even produce a level 1 file. We don't try to process it. There are some of these characteristics. Do look at the data. For instance, we have a problem with extensions that were like identically 0. Every value is 0. So there's checks like that to just make sure that there are some non-zero values in the extension. But we could add some more things here if the values are just like the mean value, it's not, it's not in a certain range or something. But that isn't happening yet. It's just mostly metadata checks on the file to ensure integrity. If it passes the quality check, it moves on with the rest of the processing. Otherwise, it's done at this stage. Next, we average like extensions. So what this means is that it has to be the same on band. So RCam or TCAM, whatever it is, has to be on band, has to be the same wavelength. Everything has to match. Basically, it has to be an identical measurement. For waves, there's just one of every measurement. For the synoptic, you have 4 more repeats of that. Okay, so those are averaged together. And this is beyond the averaging that happens already at the camera, right? So there's num sum, and that's recorded in the FITS header. And it's usually about 16. It's not always 16.
The waves is 14, the synoptics almost always 16.
Yeah.
Due to the 30 or 300 milliseconds that the Leo filter takes to relax, we like putting the num sum high.
Yeah.
But we're adding a 12-bit number to a 16, so we don't go above 16.
Right. So you can find out num sum if you're interested in, but it's an average already. Yes, Richard.
Hi, did you say the summation happened by the camera for those 16 images?
Well, by the
it's happening at the computer on the mountain.
Yeah, the computer that is taking the observations. So the level 0 FITS file already have num sum number of images averaged together in each one of its extensions.
And so this provides a 30-second cadence, does it, over when you're in these 16 images?
30 seconds is for all the wavelength
Yeah.
tunes.
So it's about like 5 seconds, I guess, then for
Yes.
one extension.
I think it's about 2 seconds per summed read of actual data collection.
Right, and then the movement of optics and things, yeah, to get to different extensions.
Yeah.
Do you have a feeling for so maybe when you're summing over these images, you leads to some blurring, you know, if there's some motion of the telescope or something
Oh, we'll
like that.
talk about that.
Later. Okay. All right.
Yeah. Ben's got a lot of issues that could happen here in his talk. So
That num sum, whatever value it is that 16 or 14 summations over like modulation states? So you
Yes.
have 4 of
Yeah.
these.
it's everything is exactly the same.
So we run through the modulation states in a round robin fashion. So every fourth one gets summed together.
Right.
And then that gets combined and written out.
Yeah, so when it's 16, you don't have 4 of each, you get 16 of each. And
It's so it's 16. We're
64.
going to take 64 images.
Yeah.
And then combine that down to 4 images. I'm doing the math right.
Yeah.
And then that's per camera. Of course.
Mhm.
And you say images for fixed files. Just when I'm saying images, I mean camera readouts. We're going to do 16 readout or 64 readouts.
Yeah.
And end up with 4 images in the fixed extension.
Oh, in the fixed, okay.
And the reason we're doing this up there is because the bandwidth up amount. So we need to somehow reduce the amount of total images we're taking a little bit.
Okay. The next step is to apply a dark. So here we have the corona after applying the dark. The darks are just subtracted from the science image, right? So the darks are in a different file from the science images, and so they're not taken at exactly the same time. So you'll have a dark taken, and then you'll go for some amount of time, and then you'll take your science image, and then there might be another dark later on. And so your time in between those 2 dark images is interpolated to create a dark that is subtracted from the science image. Doesn't display terribly well up there, but this is actually a pretty nice intensity once you apply the dark. Polarization will have to wait. The gain, so we take flat are also taken, and they're done the same way, but they have to have a little bit more matched to them, like wavelengths and things like that are matched to the science file that you're applying them to. But they're interpolated as well. You might have flats before and after you're taken. They're averaged together depending on how close in time you are to one side or the other. And they're averaged together, and then they're converted into a gain by this focal radiance that tells you the transmission of your diffuser. Yes, Richard.
Sorry to keep stopping you.
Okay, no problem.
On the darks one, you've got a bright ring around the occulter. Why do you have like the bright ring in a dark image?
In the bottom image there.
No, in the previous slide, you said the dark. You showed the dark, and it also had a bright. And it's also got bright.
I'm sorry. This is the science image after applying the dark. So the top is on band, and the bottom is the background.
Okay, all right.
And the same thing here. The top is the on band, and the bottom is the off band, the background. After applying a gain, the darks and gains themselves are kind of interesting to us, I guess, but I don't think you'd be interested in it. I don't know. I don't have any images of the slats or darks themselves in here. Okay, and then there's a camera correction. So there's some hot pixels, the pixel values that they're kind of just stuck on. And these are also found outside the pipeline. Steve has a way to detect these and gives me a file that has the locations of them. And then for each of those locations, neighboring pixels that are used to compute the value at the missing place. There's also some of these variable hot pixels that are not corrected for and cause some issues that we'll talk about later in various troubleshooting things. But sometimes we have hot pixels that are not corrected for because they change over the course of like a single day. Okay, demodulation. We take those four mixed polarization states and then apply that demodulation matrix Steve was talking about to each mixed polarization state. You get out an IQV for that pixel. So here we go from, on the left, we go from something that basically looks like intensity all the time to something that looks like intensity Q and U, and then V. And my order is always I in the upper left, and then Q in the upper right, U in the bottom left, and V in the bottom right. Yep.
Somebody's going to ask you, do you want to explain why there's signal in V? That's for Steve. That's for later. Okay, so Ben will get to that later.
We'll get there.
Someone will get to that later.
This looks pretty rough right now, but we'll keep going. It gets better. And also, these are intermediate steps from the pipeline, so I had to kind of just grab some results as I went and then display them here. They're not kind of optimally displayed for all these intermediate products. Okay. There's a distortion correction, right? So for distortion in the optics, up until this point, everything, the flats and darks and all that stuff was basically pixel for pixel from the raw image to that point, right? Like you could correspond directly, one pixel had an input to that one pixel in the product. At this point, we're blending things a little bit, but now our occulter should be ideally perfectly round so that when we go to find that occulter, we can fit it for a circle. So the next step is finding that occulter.
Can I ask a question?
Oh, yes.
So up to all the averaging and everything, we do pixel by pixel. So do you save somewhere the error that, because that sounds like you have like different ranges, I guess, no?
Oh, in the average, like so a standard deviation or something
Yeah,
from when I
like
do
that.
those
Like
averages.
pixel by pixel, like say that, oh, we have too much deviation, we have to drop out the thing.
That's right. So we did some experiments with this, and there's some engineering products that we did, like with basically subtractions. When we would start averaging things together, actually subtract them in pairs and see if we got any structure in those results. We don't have a science product for that, but that's something that we could potentially do, is that produce some kind of standard deviation from those averaging. I can't do anything about the averaging that's done on the mountain.
Yeah, the stuff at the mountain right now, we just add together and write it out. We don't do any other.
So you drop out the individual.
Yeah, we don't save the individuals at all. They're, just in memory long enough to sum them.
It's just accumulated, basically, summed up. So yeah, that sum, it's actually a sum. It's just adding together
So
accumulated
this
sums.
variation has no interest. There's no
Um,
interest.
I think there's probably some interest. We just haven't done it.
Yeah.
And, and so
And if we wrote out all the data, it would be 16 times as much data
Yeah.
as we already
No,
did.
no, no,
We take up to
no,
100.
but we can get statistics on it. Instead of,
We could, no, but I'm just saying, if we saved all the data, it would be 16 times. And
Yeah.
we average 50 gigabytes per day, up to 100 gigabytes in a day. So we'd be taking 16 times.
so in
that.
Canada, maybe we should do.
We could.
statistics.
And we could do the statistics, but
We don't.
we would have to
We
bite
certainly-
the bullet on that.
right. And
That's why we wanted to do that.
there could be, but for the averaging that I do, the pipeline does, there could be, right? Not for the waves, that would not be useful, but for the synoptic images, you could produce something.
This is a good suggestion. We can say that standard deviation if our computer is fast enough, so we don't throw that information out, and that would give us, for example, information about how good the pointing is, the image is stable, and that those images are well aligned and things like that. So the reason why we do the summing, there's basically two reasons. One is, as they're saying, it's the amount of data. So you want to be with that becomes manageable. And the other is one single frame. If we have no summing at all, that would be noise. Because the camera is only at maximum exposure times, and it's not enough signal for noise in most people. There is a practical reason doing that. Now, Ben could probably say more about that. We can change that. We can change the now some. And we have done in a few cases. We have taken data with no summing at all to look at those. So we can experiment with that a little bit for daily operations, just convenient to do some summing with the camera.
I think you just double your size, then you just save the image. And
Yes, it depends on computer time, but I think may be able to save it that, and that may be also information for quality of credit. So I think it's a very good suggestion.
Yeah.
Yeah.
I mean, it's possible. The one issue is that you'd have to have a bigger data because you can't fit the data in size.
I mean, there's some engineering work to do to make it happen.
Doesn't that mean, is it possible to get a different camera that can handle a longer exposure time rather than just 80 milliseconds and then doing,
Ollie?
16?
Possible.
Is that a legitimate, as much of a, joke as it is that a legitimate, not option, but does it exist?
It doesn't exist off the shelf the way cameras were purchased off the shelf.
Oh,
You'd have to get
any of those?
custom cameras, and Ben's probably not far off in his estimate of the cost. But yeah, we would love to have longer exposure times.
And I
But
think
it's not,
it's manufacturer we bought these from on their smaller cameras, they're doing lower noise and slightly longer integration time, so
Yeah.
it might be possible, but
it turns out that there's a full well depth of the detector as well. How many detected photoelectrons you could, and these cameras have only about a full well of like 15,000
That's
electrons.
the fundamental reason why it's only 80 minutes. We all only choose 80 milliseconds.
It's the maximum that
Yeah,
they're allowed to choose, but I'm saying if we had a longer exposure time, we'd saturate cameras on like 10.74 or some lines.
Yeah, and I'm saying, is there a way to get a camera that has a deeper depth?
Deeper depth and longer exposure time, not off the shelf, but
So those are two primary variables that cause all of this numb sum stuff, averaging on the mount itself.
I suppose, yeah.
Or at least it's the root of,
And here's the thing though, if these cameras have a readout noise of 40 electrons. And photon noise goes to the square root of the number of photons, which is to say if you have 40 square, 1600 detected photoelectrons, and our full well is 15,000, and you're kind of getting into the photon noise regime. So readout noise is much less important if you're filling even those 15,000 electron wells. So averaging frames doesn't incur a lot of a penalty. You'd love to go with longer exposures and bigger wells to avoid read noise in all those readouts, but it's not maybe horrible. But yeah, we definitely would love longer exposures. And deeper wells. And for Cosmo, we're hoping to do that. And for Cosmo, we're also hoping and planning to save every readout, all the data, no matter how huge it is, which will be quite large. We're talking about 4K by 4K detectors. Here we have 1280 by 1020. Go ahead. Sorry.
No problem. So at this step, we're trying to find the occulter. We have options in the pipeline that view this finding the occulter step at various places, kind of settled on this location. Be good. This finds the occulter, but it doesn't actually process the image in any way. It just records a bunch of information about the center and radius of the occulter. So that's what all these keywords are. Radius keyword in the primary fit center might be of interest to you because that's the radius of the occulter. And so that might be of interest when you're masking images or things like that. Also, the chi-squared from the fit is in there. It's the fit chi-01, and that's a measure of the GBU measure that we'll talk about later. So a measure of quality, right? So if it found that center very well, then hopefully we can combine the two cameras very well.
I have a question. How do you find what's the algorithm used to find you?
Yeah. So let me go one more slide here. So basically, the radial derivative is computed, and that finds those, and then the maximum of that radial derivative. So on every radial line, that finds those red points out on the outside. Those red points are fit into a fitting routine that is looking for a circle, and then we find circle. You barely see the outside yellow, but there's an inside yellow and an outside yellow band. That's kind of our band of where we're looking for the occulter in, right? So kind of restrained where we're looking for, and we have an initial guess, which is the thing in the middle there, that little bear across there.
Thank you.
Yep.
Ken Reardon had a question.
Oh,
for the chat.
I'm answering it here.
Okay, yeah. Okay, so but nothing's under the image here. This is just a engineering diagnostic that we output to check our centering. Then we could do the continuum subtraction. We just subtract the off-band image from take the on-band image and subtract the off-band image from the in the same camera at this step. We haven't combined the cameras, so we have to stay inside the camera that you're doing it. So our cam for every wavelength will get subtracted, and then there'll be a T-cam subtraction for every one. And this is also in a step someone had asked about where that background extension comes from. We just save it here. We subtract it, but we don't throw it away. We keep it, and then that'll end up in one of the extensions later on. There's an option to do this or not, and it's turned off for 1083. And if you want to know more about that, talk to Momo about that. It's a science question. And then here we've done continuum subtraction. So again, our IQ U and V intensity is still looking pretty good. U and V still not looking great yet. But we're heading on. Next, you might notice that there's if you go back here, you'll notice that there's some vertical bands in the image. Oh, yeah.
Mike, question on the previous
Go back.
thing. When you compute the center, do you save it anywhere or just the offset values?
That center. Okay, so we save the offset values in the raw image. So that's from where the raw center was to where we think the center of that image should be. When you get to that level, the final output, those images are centered. So the center of the image is the center of the array, right? So this is an offset. It'll be hopefully 2 or 3 pixels or whatever. Just we had it pointed basically correct, but it was just a couple pixels off one side or the other.
It's in the header.
And it's in the header. It's saved in the header.
It's all in the header.
Yeah, but it's an offset, not a absolute location.
So there is nowhere, not even in the intermediary products, where you can find the actual that value, right?
You can find that value. It's in the header, but it's an offset from. So, for instance, a raw image is 1280 pixels, right? And so if it reports here that the offset is 2 pixels, then you'll know, okay, well, 1280, half of that is 640. So you'll know that it was at 642 is where we found the center to be. And then I showed you what this looks like. So after the continuum subtraction, you'll see in the polarization, you can see these bands pretty clearly, these vertical bands. So we have a step to remove those stripes. And this is just some averaging. You find a median value over kind of a vertical or horizontal band or vertical band, and then track the mean and remove the bands. You can still see remnants, like little tiny things if you know what you're looking for. If you go back to the other one, I can't really change slide very fast here. Yeah, and then I go back there. Right. But it's pretty good. It removes the bands. Okay. Now we apply the alignment, right? The centering, finding the center that we did before. Now we do one interpolation that recenters it and rotates it so that solar north is upwards. Okay. So up until now, the post is basically going to always show straight down. But as you apply this alignment, you'll see that the post starts moving around, right? Because solar north is up. This is all just one single interpolation. So that's what we got now. You can see that the post is a little off at an angle, but depending on what P angle was for this day. All right, and then we combine the cameras and taking RCAM and TCAM, and at this point, this is the simplest step in the pipeline. Is just you have two things that are centered; they're all equal. You just average them together. We've been averaging as we go here. So for in a waves program, you're averaging two things: RCAM and TCAM. So this is a really nice. At least we get some averaging. For a synoptic program, you've already averaged, four things together. The first step. Now you're going to get double that to 8 extensions that are in the synoptic program are getting averaged together in this step, but it looks a lot better.
Yeah.
Bye-bye, still.
Well, you got-
That's the advantage of
Yeah.
having this dual beam
Yeah.
where you can remove these things. When you combine the beams, which you see there, is you remove a lot of issues associated with.
So Mike, you go back to the one, that you don't have the camera combined with this display. So if you look at a beam, you can see close with you see there is like a halo, which is dark in the image, in the bottom one, and it's kind of bright. And this is because you are subtracting the continuum of the same camera, which is not exactly simultaneous. And during that, even if it's a very short time difference, the atmospheric scene has changed, and this is basically the effect of the atmosphere. So by combining the two cameras, you have one image, which is a schedule on the coronal line, and one continuum which is seen simultaneously. It's from a different camera. So when you do that, that change in atmospheric scene goes away, and then you can go back to the final product. You can see they have much clearer signals. So you remove a lot of this atmospheric contamination of your polarization.
Including the aerosols.
Explanation of why.
Yeah, exactly. Including the aerosols. You had some aerosols.
Yeah.
Including some aerosols. So this step is a very important one. I mean, this.
That's the value of two.
That's the value of
dual
having
beams
the
right there.
So yes, you can do
Big
it with one
difference.
camera, but you will get a lot more contamination for your signal in your stocks. And it's also not in intensity, but not as visible, but it really contaminates. I feel
Okay. We just have a couple other transformations here. We do a transformation on Q and U. And this is the transformation that I think makes it not necessary to be done in forward. So the P angle, this is adjusting for the P
Oh, right,
angle.
In some of the old
and-
data products, we didn't do this stuff and so
That's
we
right.
did it forward and I've now
Right.
moved it for UCoMP. Yeah.
So that gives us, with Q being, positive out to the left to right and negative up and down, right? And then 45 degrees angle from that for U. So this is only affecting Q and U at this step, but it aligns. It's not a geometric rotation. It's a rotation in the Q and U space. I don't know. Yeah.
The Stokes coordinate.
Yeah.
For people who aren't aware of IQUV, I is intensity. Q is polarization horizontal minus polarization vertical. You got a linear polarizer. And U is at 45 degrees to that. V is circular polarization. It creates sort of an orthogonal polarization coordinate frame, IQUV essentially. I know it sounds a little weird to have, but they're Q and V are net polarizations, and they can be positive or negative. I obviously has to be positive, but Q and U can be positive or negative, so they're net polarizations. Q and U linear and V circular.
And then we get the kind of level 1 FITS file that we were mentioning at the end. So at this point, we write down a FITS file, right? And we make some quick look imagery of that, right? So we have an intensity GIF and an enhanced intensity that has image processing algorithm written on it to enhance contrast. We also have some products where like I've been doing the IQUV, But then this is an all wavelength, right? So you get everything that's in a file, basically IQ, U, and B for the 3 different wavelengths that are in the file.
Mike, can you point out if the gzip files that are on the webpage contain these?
Yes, so there's a zip file that contains basically everything, all the quick looks, right? Then you can get everything for a day at one time by wave region. So you get all 1074 quick looks, I believe, or is that right?
Yeah, you get,
Yeah.
there's more in the gzip
yeah,
file
there's-
than the imagery you're seeing.
Yeah.
So if you download the gzip, you'll get stuff that's.
That's right. It's manifests everything. Right now, that quick look file is not by wave region. It's just all the quick
Everything.
looks for the entire day, every wave region that we are publishing. Steps that we don't do now that we might or maybe have eliminated, and that's the camera linearity that we do for some other instruments. We did some exploration with that. It doesn't seem to be necessary. There's a despiking that we talked about with some of the hot pixels that are variable, right? Like you might want to find those on the fly and do some kind of correction for those because they cause some problems for some of the other level 2 products. And then a sky transmission correction that we have a brightness in sky at when the flat is taken, and we might want to normalize it, the science images by that brightness from the flats. Okay, but none of these are currently done and probably aren't going to be doing the camera linearity, but maybe we'll do the other 2 at some point. But we have
to do the
sky transmission, right? The despiking, we're still playing around if we can do that well. The sky transmission would be straightforward. At this point, we want to do a quick check of the quality of that file. So we run through some things, some conditions here. These are mostly based on the data at this point now. And so we measure that background image that we talked about, make sure it's in a certain range. This is by wave region. So for instance, for 1074 here, good backgrounds are deemed to be between a median value of the background between 5 and 30. And so if it's below 5 or above 30, we count it out for the level 2 processing, right? So if it fails the GBU, it's out for the level 2. That first column there, reason, is a bitwise kind of sum of the conditions that that it failed. So 0 means it's good, right? It had no reason to be bad. If it 16 means condition 16 there failed. If it would say 3, that would mean that condition 1 and 2 failed, right? So it could have multiple things failing. We eliminate them at this point here. We're looking at things like the background value, the V signal, the chi-squared of the fit that we did when we found the occulter. And sigma is the number of standard deviations from the median image that you are, that image is from the like images, like in the same program. Okay. So if it passes the level 1, then we move on to the level 2. Here's the dynamics. Again, this is for all the published wavelengths. Those are the 5 published wavelengths. And an example file name. This is the file that corresponds to the file name of the level 1 file that we just processed. It has the word dynamics in, right? And now it's 1074.L2 dynamics. And we talked about the extensions that are here, all related to intensity. And again, all the published wavelengths get this. And these are some quick look images for that. So for these ones that have various products like this, we get a dashboard image like this, and each one of those individually is a full size 1280 by 1024 image in the quick looks. And then the polarization file.
I have a question.
Oh, yes.
So for the Doppler velocity, the solar rotation is not removed in the pipeline.
Mm-hmm.
Is that right?
The rest wavelength is subtracted, but we don't do the
No, we don't,
correction.
no, the rotation, whatever it is.
you can basically see it in a lot of these quick looks. The right side of the sun is sort of rotating away, so it's redshifted
Yeah.
for the most part, and the left side is towards us, going towards us. So it's predominantly blue shifted. If you scroll through a bunch of quick look images on the website, you would notice that consistent pattern in all of the Doppler velocity.
Yeah, when I'm dealing with this, I usually use the polynomial fitting to remove the polarity, so that we can have a more. We do not see this blue and red pattern in the final Doppler velocity, because I haven't tested if I'm using the original Doppler velocity to do the wave tracking, what the result could be. I have not tested that. Yeah.
Polynomial fitting you're doing, is that the one that we can,
But yeah, kind of like that.
kind of like that? There was a question, I thought, with that there's solar cycle effects behind that, the polynomial you have to subtract might vary with the solar cycle.
I don't know, because there are not enough data to
Yeah.
find the pattern. I don't know. I'm not sure about that. I just
The reason why we're not doing that correction for count either at this point. And the reason that in a perfect world, that should find the solution. But in reality, we'll see that in the artifacts, especially later. Our velocity is very sensitive to systematic errors and stray light. So we have times where we see one side that is one color predominantly and is not this reputation. We think it's due to some kind of stray light contamination, and you'll see velocity there that are 4 or 5 times what this rotation should be, or even bigger. So basically what that algorithm was doing was removing this kind of systematic difference between the two indices in the detected frame, and not with the real solution. So this is why we have decided not to do it. But if we can get data that don't have this systematic, and there are times when the instrument works very well and they look very clean, then you can go back and get that. I think somebody.
Yeah, Jyoti asked a question. Someone asked a question online.
Yeah, actually, it's on the same line. So it appears that there is asymmetry and there is a predominant redshift in one end and the blue one. In fact, I looked at Jyoti's, one of the other data sets she looked at. There also the similar effect is there. Isn't it the rotation correction is still not fully sort of adopted? Was that clear, my question?
I'm sorry, I was looking at the chat. Kevin's question.
Yeah, the question is again about the asymmetry in the Doppler shift. So it looks like, predominantly red in one end and the blue the other end, which doesn't seem to be real, which can affect, which can be because of the non-compensation of the rotation appropriately. And this is just not this particular thing. I have seen Jyoti's presentation, and I see that she also has that effect.
So if I understand your question, the red to the right and the blue to the left is mostly the rotation of the corona.
Yeah. So can't it be corrected?
Well, it can be corrected, but it's a little difficult. It turns out that all that other stuff there's a lot of velocities that are not associated with rotation, and they're as large as the rotational component. So it can, and there's a paper that Hui Qian was the first author about CMEs where he removed the rotation with some kind of an ad hoc kind of correction. So it's possible to remove it, but there's a lot of other velocity stuff going on there, and that's exciting. I mean, that's what's neat. There's all kinds of velocity things going on. Flows are just rampant all over, and they're large. They're multiple kilometers per second kind of flows all over the corona. It's like 5 kilometer per second flows. So there's a lot of stuff going on.
So is it fair to say, I mean, it depends on, if we actually knew what we should expect of the corona, we might be able to subtract it based on physical knowledge, but I believe Town's algorithm had to do with it, looking at a lot of data and getting a pattern, to fit. And the question, and then there was some questions raised about whether that would be uniformly applicable. And so there's a question about how to do it. And because of that, I think the decision was made to serve it without that, but that's not to stop anybody from then applying a post filter appropriately. Maybe see how you could, I don't know if I represented what you do quite right.
Yeah, actually, I'm doing that day by day.
You do it day by day.
Yeah,
Okay.
I'm not finding a uniform path.
Okay, all right.
And the good thing about the waves is they're oscillatory, so they can be offset to the blue on the
Yeah.
west limb, to the red on the east limb, but they're oscillatory. So ultimately, if you filter the data, then the waves come out.
Yeah, I think for wave tracking, the absolute value of the Doppler velocity does not matter. So
Yeah,
even
because they're
very
looking at relative, yeah. But I was just also looking at, earlier comp data guide, you did have a correction on the, on the rotation, and then it removed this asymmetrical red and blue prevalence. This was earlier in the comp data, I think you were using it.
Yeah, and we kind of decided, well, maybe people are interested in that, and we should remove it.
So maybe this is something we could bring up again
Well,
on.
the main reason was that we were removing the stray line.
Yes.
This is what I'm talking about, where there are artifacts like this.
So perhaps, can I suggest that we bring this up again later this week, especially Friday? Because there could be
Yeah, I know people ask.
there could be a program, some software somebody could develop that can be served with the data. So if we come to a consensus of the best way to do this, so that we can provide this software to do a removal, and maybe we can work with you, see how to, and people could use it then. But I think the idea was to serve the data without that until we're totally happy about how it's removed.
Yeah, so if I can just finish here, there's a couple more products that I just want to mention that we have, and then we'll talk about more of these in detail as well as back them in other locations. There's a polarization file. Again, this is only for 1074 of the published data right now. And I mentioned these before, but you get some intensities, but then you get QUL and then azimuth, radial azimuth, and get a dashboard of what those look like in each of the individual images as well. The FITS file will have Q and U and L, but the image here, the images on the quick looks will be normalized by I. And then we go to this other step of, so those are all by level 1 file, right? So the level 1 file corresponds to those. The mean and medians average up everything from a program, right? So like all the waves 1074 get averaged together into a file. This looks just like a level 1 file, except it's an average for each one of the extensions. And then corresponding to every mean and median file is a quick invert, which has basically the same kind of processing that we get in the dynamics and polarization file, but for an average for the day. Okay, so 8 extensions with both intensity and polarization type products in there. And again, a quick look, and then there's individual quick looks as well. Try and find what you're looking for. One last thing, we have temperature maps from two varieties of temperature maps, combining wave regions together in a single image for a day. They're currently only available as quick look PNG files. They're currently only made once per day as a daily image. We're thinking about producing a movie of these throughout the day, so we'd have images throughout the day and providing FITS files instead of just quick looks for these. But here's 2 examples of the quick look versions of those files. And I think I've got one more thing. Yeah, just the feedback. Same as before. Has my email address. MLSO data request is a good place to send to a bunch of people to get data in our GitHub info. Stop it. Recording? Yes.
I know, it's a break time.